Swayam Prabha. Digital India. Educated India.
So today's discussion is on control chart of range and tolerance. Let us say there is a parameter theta which is basically the range, is indicating the range. Range is the difference between the minimum and the maximum value. Suppose you are testing yarn which is in a cone and you have taken, let us say, 5 or 6 pieces of yarn and then you have tested them. So you have basically 5 or 6 reading from the same cone or same package. So the difference between the minimum and the maximum value that you have got while testing 5 or 6 pieces of yarns, that difference is the range. The distribution of sample range even from normal population is not normal. Therefore, the previous control limits cannot be used for range. Range indicates the variability. The lower the range, the better it is. So like variability we can express in terms of standard deviation also. The range also can be used as an indication of variability. Now, because they don't follow the normal distribution, therefore the control limits are different, and these limits are stated here. The action limit is dn r bar. R bar is the average range, and the other one is dn dash r bar. Warning limits are cn r bar and cn dash r bar. So what is these constant dn, dn dash, cn, cn dash are given in a table, and that table is this table. These are the values of cn, c dash n, dn and d dash n for different values of n. 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the different values of n. That is how many specimen I am taking from a particular bobbin and then testing for strength. So that is what is small n. Or how many readings I am taking at a given time from the process. That is small n. Then I can take the readings after a certain interval of maybe 2 hours or 5 hours or 6 hours. So every time I am taking a reading, I may be taking 4 or 5 readings at a time. So this is how many readings I am taking. That is also is small n. So if these are the action limit and warning limits and the values are stated, so therefore it is very easy to calculate the control limits for range. And we are going to look at this example and then see how the range can be, the control limits for range can be calculated. These are very easy, the calculation part. So here is an example where the data is shown is the means of 25 samples, each consisting of 4 test results. Use the data to find central line and control limits for range. Not X bar. X bar actually we have done already in some previous slides. You will find that, but now we are taking the same examples and we are trying to find out the control limits for R, that is the range value. So here, for so many samples, 1 to 25, the range corresponding range values are given. For sample 1, range value 2.7, sample 2, range value 3.1, like that. 25th sample, range value is 2.4. And the range value has been calculated based on how many readings? Based on 4 test results. So, whenever we are doing the test for each sample, we are doing 4 tests, and the difference between the minimum and maximum is the range, and these are the values of range. So you can see the range values are varying between the minimum one is 1 and the maximum L, it appears to be 6.5. So for different samples we get different values. Now what we need to do is to find out what is the average range. So these are the individual ranges. Average ranges, we have to sum them up. So when we get the summation of the ranges, it is 73.7 divided by, it is n. So n is 25. So therefore the average range is 2.95 in this case. So that is the value of average range. After this, we need to finally draw the control chart. Therefore, my center line is going to be 2.95. That is the center line. Now, we have to find out the limits. So we know the formula of limits. Action limit is dn r dash and dn dash r dash. Therefore, and warning limits are cn r dash and c dash r dash. So this is already stated earlier. And these are the values of dn, d dash n, cn and c dash n. These values are also given in many statistical textbooks, wherever the quality control chapter is there, control chart especially chapter is there. There you will find these values of cn, c dash n, dn, d dash n for very different values of n. N 2, 3, 4, 5, 6, 7 like that, for different up to, it can go up to 10. So these values, standard values, are stated in these tables. So we have to consult this table. Without that we cannot remember this data. We need to consult. So action limit, first of all, dn r dash. So this is simple calculation. The dn value we have to find out for n equal to 4, and that value is 0.10. So 0.10 into 2.95, that is what is my r bar. So r bar is 2.95 average range value. So dn r bar 0.10 into 2.95, that is going to be 0.295, and d dash n r bar is going to be 2.57. You look at this value. This is 2.57 into 2.95. This is the value of average range. This gives me a figure 7.6. And then we go to the warning limits calculations. Similarly, cn r bar. So we find out what is the value of cn when n is small n is 4. For 4, cn is 0.29. So we write 0.29 multiplied by 2.95. That gives a figure 0.85. Similarly, c dash n is 1.93. We write 1.93 and multiplied by 2.95. So 2.95 is a constant, which is the average range, and we are multiplying that with the constants cn, c dash n, dn, d dash n, and I am getting these values. These are the action limits and the warning limit. And we also have the center line where it has to be drawn. Now once you have this data, now the job that is left is to create this particular chart. So for this particular chart, we can make it using scale and pencil, or one can also use the Excel sheet, and on the Excel also you can plot this data points, individual data points, that is the values of individual range values. If we plot them and join them, we get a zigzag type of curve, which is the this particular curve is basically showing you the way the range values are changing from sample to sample. And then the mean is located where the mean is 2.95, that is somewhere here. So this is close to 3. So this is the central line. This is 2.95 exact value. So let us say it is 3. So we draw a line at 3, and to make it permanent, we have given a red color. So that is the central line. Now we write what is my action limit. So on the higher side it is 7.6. So around 7.6 we draw this line. So this is upper action line or upper control line, whatever we can write. And then the lower line also we have to write at 0.295. So around 0.295 we have to draw another line to get the value of the D-R bar. Warning limit also 0.85 and 5.70. So this is UAL, that is WAL. Yes, this is upper action limit and this is warning action limit, so WAL. So on the higher side it is 7.6 and this 5.70. So at these two locations you draw the line. Similarly, on the lower side you draw two lines indicating the lower warning limit and lower action limits. And now we can see how the data points are varying. So we can see that the data points are mostly lying within the action limits. None of them is going outside the action limits. So this somewhere it is, one is that though they are fluctuating, but still they are within the control range. Therefore, the range values are, we can say, they are within our control. That is how we can make a chart for range. And if we see the points are close to the center line, the closer they are, the better it is, then the variability will be less. And further they are from the center line, and with variability is more. But variability will be always there because of random variations in the process, which some of these causes of random variation we are not in the position, or we may not be able to completely get rid of them. From there we go to the next one, that is tolerance. Modified control limits for average. When tolerance values are given. In practical situations, tolerances are commonly used when the property is a continuous variable. Generally, you will see that if you look at the specifications of many products, you will find that tolerance is given. Tolerance plus minus 5%, 2%, 1%. So in most of the textile material also we give tolerance, because we know that there is some amount of variation which will be there in the process, which will be beyond our control. and therefore some minimum variation is always expected. Example, suppose yarn count we write 30 plus minus 2 ticks. That means the count range is 28 to 32. So as long as the count being produced is found to be within 28 and 32, we'll say this is an acceptable yarn for further processing. So this tolerance plus minus 2, some companies may say plus minus 1.5, someone can say plus minus 1, but the lower the tolerance, the more difficult it will be to produce yarn which will be lying within that tolerance limit, because the random sources of variations are difficult to control. In the case of yarn, it could be because of change in properties of the fiber, it could be because of some disturbance in the machines, maybe wearing out of the machines, that could be operator to operator, differences could be there. The conditions of the machines producing a yarn also may differ from each other. If we not produce yarn from one machine, we produce on multiple machines the same count. Then the spindle to spindle variation could be there in terms of the variation in the drafting systems. So there are many reasons which can cause some amount of variations in the properties of the yarn. So that also it is on the count part of the yarn. Okay, but therefore a tolerance, a typical plus minus 2 take, sometimes tolerance is given plus minus 5% or 6% or 4%, and as long as the product, that particular parameter remains within this tolerance, it is generally acceptable. Let us assume that a process is under control and the sigma of the random sources of variation is known. That is, the variability is also known to us, that how much it will differ, how much it will vary when the process is under control. So individual articles will be accepted as long as the parameter theta, if mu s remains within this range, mu s plus minus t. So mu s is the, theta is the property in which we are interested. It could be count of yarn, it could be text value, it could be the strength of yarn, it could be the GSM of a fabric, it could be the length of a fabric roll, whatever it is. And mu s is the mean, and plus minus t indicates the tolerance, the absolute value tolerance. So tolerance is therefore become plus minus t, so it is becoming therefore 2t. Now whether or not the control chart needs modifications depends upon the ratio, which is 2t by sigma, and this is known as relative precision index. We will know more about it now. Here you can say we have a process whose mean is lying here, is that parameter whatever theta is, and then we have put the upper tolerance mu s plus t, which is here, and mu s minus t, which is here. And this curve, that Gaussian curve that we see, is indicating the distribution of individual articles or items. It could be whatever size, it could be strength, it could be fineness, whatever it is, chemical distributions. So distribution is shown. This is the distribution curve. Here is the mean of this, and mu s plus T and mu s minus T. T is the tolerance. So where the tolerance lies, they are also shown by upper tolerance and lower tolerance lines. All right. When this, and this is also shown for another, same thing we are showing at the bottom, where the distribution of the individual articles is very narrow. Here it is very, very wide. In this case, it is very, very narrow. You see the spread of the curve. It is quite narrow. Therefore, in this case, 2T by sigma will be very, very high. Narrow basically means sigma value is low. That means variability is less, standard deviation is less, but the value of T is fixed. If the standard deviation is less, T by sigma, this ratio is going to be very, very high. So here is a situation which indicates a process where T by sigma is high, and here is a process on the upper diagram where T by sigma is low. That's the difference. So in this case, the spread is more. In this case, the spread is less. Now, what can be done? Reduce process variability. If this curve looks like this in this case, so we can say that here is a region that is some articles values are supposed to can fall here, and therefore even though the mean may be at the right place, but since the distribution is quite wide, some articles are going to fall in this region, and therefore some percentage of articles or items being produced will be rejected. So they will be in a way defective items, and therefore they will be rejected. Now in this case, if we want to improve the situation, what we can do? We can reduce the process variability. That is, if I can reduce the spread, that is what is shown in this diagram, that here in the lower diagram, the spread has been reduced. So one thing is reduce the process variability, check whether the tolerance has been set narrowly than necessary. That is there any possibility to widen this tolerance? The tolerance is too narrow, then obviously more and more articles will go beyond the tolerance. So the tolerance can be widened, then obviously less and less articles will fall. So these are the things which can be done. Reduce variability, or tolerance reduction possibility is there or not. Sometimes tolerance are set arbitrarily and maybe too stringent and not justified in practical terms. These kind of things may happen, that we are producing some count and we say tolerance is just 0.5 tex. This is a too stringent type of tolerance that we are given. Something which is almost very, very difficult to produce, or it can go beyond the capability of the process. We will never be able to produce. So this could be, therefore, sometimes tolerance is too stringent has no practical sense. Sometimes the tolerance, there is a possibility the tolerance can be increased without affecting the performance of the product that we are making, or if possible, sometimes we have to reduce the spread, that is variability, or reduce sigma. These are the things that we can do in order to take care of the process, so that too many articles are not produced, no defective articles are not produced. When neither can be applied, it is better to keep the control chart for averages of conventional type, and it will keep the average level of the process correct and remove the defectives produced by 100% inspection. That is, when none of these approaches can be taken, Then we allow the process. This is our we keep the control chart for the averages of the conventional type. That is, we say that this is plus minus 3 sigma limit is the range in which you are trying to keep it, and the articles which are becoming defective, they will be reprocessed. But this may not be possible in many situations, that we cannot really reprocess if by producing some yarn, and some counts are becoming too heavy or too fine. We cannot make the, once the yarn is produced, the coarser count cannot be made finer, or finer count cannot be made coarser. This is something which is impossible. But in so in that cases, what we can do, reprocessing is not possible, so we can reject. So rejection is possible. So we can, defective items can be rejected. That is, if that option is valid in a given situation, that can be done. In the case of producing sweaters, let us say the length is or the size is defective, and therefore if we are trying to make a certain size, or some size, suppose is medium size sweaters we want to produce, and we are finding that according to medium size, whatever dimensions that we should have for the length and shoulder area and the sleeve, if they are not coming correctly, then we can say they are defective items, and therefore they are segregated and they are removed from the items produced. And we can, that's what is known as 100% inspection, that we go for 100% inspections of the item that we produce in the case of garments, and then we can remove the defective garments. So whatever will be left, they will be acceptable. So that can be done. If relative precision index is high, no defective items will be produced. So in this case, you see the spread is very, very narrow, and the limits, the tolerance limits are here and here, which is far away from the mean of the distribution of the parameters of that particular article that we see. It is quite narrow here. Therefore, in this kind of situations, there is no chance that defective articles would be produced, because the tolerance limits are much away from the mean value of the parameters in which we are interested. The parameter could be strength, parameter could be elongation, it could be thickness, it could be GSM, whatever it is. So in this kind of situation, let us say B, we are quite safe. That is, this is because the tolerance is much larger in comparison to the variability in the product or in the process. Modified control limits will continue now. When the process variation is low, the process averages can be allowed to drift from the mean till it starts producing too many defective items. Let us say the case here. The first thing is this, look at this orange color, this normal distribution of a particular parameter. Now, when it is at the central locations, the spread is from here to there, but the tolerance limits are far away. No, it is here. This is tolerance, upper tolerance, this is lower tolerance. So if the spread is like this, as shown by the orange color curve of a particular parameters, then as long as the mean is here, there is no chance of producing any defective items. But even we can allow the process to shift towards the right hand side or towards the left hand side. And even if shifts, how far it can shift. The two extreme shift positions are shown. One on the left hand side of mu s, other on the right hand side of mu s. So as long as it is shifting, no defective items are produced till the curve is going to cross this threshold line, that is of upper tolerance and the lower tolerance. So if it starts shifting on the right hand side, left hand side, and when it reaches this point, that is the mean reaches this point, then you see part of the curve is going outside that mu s plus t line, that is the tolerance line on the left hand side of the curve. Or if you think the other way on the right hand side, then also the maximum seat is up to this much, and here also it has gone and producing some part is defective items are produced. So if we allow that the defective item that will be produced we are acceptable as long as it remains 1 by 1000. Therefore, this area, that means this area is 1 upon 1000, that is 0.001. So as long as the curve keeps shifting, and let us allow it to cross the lower tolerance limit, and even it crosses to some extent so that we produce at the most 0.001 proportion defectives, it is acceptable to us. That means this area is 1 upon 1000. In every 1000 articles, 1 article may be defective, and that is acceptable. So you can say this area in this case is 0.001. On the other side, this area also is 0.001. So that means if this statement, given this is acceptable to us, the allowable shift is from this location to these locations. That means, let us say, the process average will be allowed to shift by how much? From here to there, and that is, this shift is plus minus 3.09 sigma. 3.09 is standard normal variate corresponding to the tail area 0.001. When this area is 0.001, then corresponding to this area, the standard normal variate, that is Z. If you take Z alpha, while alpha is 0.001, the corresponding value will be 3.09. So for that case, the limits will be now how much? Mu s plus t. This is the original tolerance, mu s plus t here. So we can allow the mean to shift maximum to this much, and therefore tolerance will be mu s plus t minus 3.09 sigma. On the other side, it will be mu s minus t plus 3.09 sigma. These two are the lower and the upper limits of average. That will be our modified control limits based on this particular conditions of accepting that 1 in 1000 items, if it goes out of order, we will be accepting it. So as long as the maximum, the mean of this process mean will be allowed to shift is going to be 3.09 sigma on the left hand side and right hand side. So the new limits are going to be mu u upper and mu l for the lower. Now we go to the next. Again the same curve, and we start from the beginning, that is, the process mean should not go beyond these two limits to avoid generation of too many rejected items. So that is the maximum allowable drift of the process mean. Here also the same process is being shown, but now what happens that there should be a high probability to take action whenever it goes beyond this limit. That is okay. High probability should be there. The action is generally based on sample of size small n. How do I know? So every time, just to know whether the mean has shifted or not, what we do? We take a small sample of size small n and find out what is the mean value. So our decision criteria is based on the mean of the samples of size small n. So when the process mean shifts by lambda u, not mu u, corresponding distribution of sample average is shown. These are the distribution of sample average. For the same, this side is distribution of individual items. The right hand side, the curves are distribution of sample averages or sample mean. We all know that sample mean distribution will be narrower than the actual distribution of the samples. Why it is narrower? Because it is based on mean value of n number of items drawn from the populations. And the standard deviation of the sample of size small n is always sigma by root n. The higher the value of small n, the lower and lower will be the standard deviation of the mean value. And we all know, we have already studied that standard deviation is of the mean is also known as standard error. That is known as standard error. Therefore, for the same curve, the distribution for the sample mean is this. That is what it is showing. This is the sample mean distributions. Now let us take 95% chance of taking actions when the maximum allowable drift has occurred. That is, automatically it means 5% chance of not taking actions. Say we are saying that 95% chance of taking actions when the maximum allowable drift has occurred. That means when the drift of the sample mean has gone from here to here. From here to it has gone there. This is the maximum. And let us say now 95% chance of taking actions when the maximum allowable drift has occurred. The sample mean distributions are shown, which is narrower. The action limits would be set at what level? At 1.64 sigma by root n inside the drift limits. Why it is 1.64? Because once the mean has shifted, the chances of rejecting is going to be how much? 5% of chance that it will be, even though the mean has shifted, we are not taking actions. A 95% chance of taking actions when the maximum allowable drift has occurred. So 95% chance will be that we will be taking actions because the mean has shifted. And 5% chance will be an error that even though it has shifted, that we are not taking actions. In that case, the action limits will be set at 1.64 sigma by root n, and this 1.64 is coming because the standard normal variate for 5%, that is 0.05, this area is going to be 1.64, which can be found out from any if you go through the standard normal distribution chart, which is there in most of the textbook, you will find that the value of Z is 1.64 when value alpha is taken as 0.05. That's why it is 1.64. So upper action limit will be the previous one minus this side. So it will be, the dotted line is showing where it will be located. It will be located how 1.64 sigma by root n. This much is going to be the difference between the previous limit and the present limit. Because the present limit is based on the sample averages. The earlier limit is based on the individual samples, but now it is based on the average, and therefore the value is mu minus 1.64 sigma by root n. So we write it, mu is equal to mu s plus t minus 3.09 sigma. We have already seen it earlier, and we put this value 1.64 sigma by root n. Mu s plus t we take together, and from these two we take sigma common. So we take out sigma. What is within bracket is 3.09 plus 1.64 by root over n. Now the sigma and r bar are related, that we have also seen earlier. The range and standard deviations are connected by a formula. Sigma is an r bar. So upper action limit is going to be, sigma will be changed by an r. We will change the sigma, but same equation we are just writing, replacing sigma by an r bar. And now what we are doing, that if we mu s plus t we keep it within bracket, r bar we separate it, rest of the thing we take together, 3.09 plus 1.64 root over n into an, and we call it a new factor a dash n, capital A dash n. That is what we write this. So that it becomes my upper action limit, which will be somewhere here. And the lower action limit, we follow the same steps, and we get, this is the value will be for mu s minus t plus a dash n r bar. That is going to be the lower action limit, and therefore action limits are going to be mu s plus minus t minus a dash n bar. If you look at these two equations, upper and lower, I can write this way, mu s plus minus capital T minus a dash n r bar. It is basically rewriting the same thing in a different manner. So there is no difference. If we keep this one, it is still okay. There is no difference. So what is mu is stated here. What is mu well is also stated here. And the new action limits are actually based on sample averages. Therefore, they are different. These are the limits. These are which is not based on sample average. It is based on individual articles or individual items. But if you want to base it on based on average of few samples that we draw, then the limit has to change, and these are the new limits now. And the values of a dash n is given here for different values of n. This table is also available in many textbooks, and I have given a reference previously on the book of G.A.B. Lip, Same textbooks also gives these data are there. So this book or any other book, if you see, you can find out if the control chart chapter is there, you will be able to get these data. So these data are in a way is meant to quickly get the solutions, especially when you are using calculator to find out the final results or doing the calculation using calculators to make the process of finding out the solution faster. Now we are going to look at an example, and this example is that specifications of nominal linear density of yarn is 36 plus minus 2 ticks. That is what is given. 20 samples were taken at regular interval and 5 tests for linear densities were conducted on each sample. That means I am taking 20 bobbins at some intervals. I am taking it, and then from each bobbin I am doing 5 tests. That is, we can think this way also. It is not the 20 bobbins from the same machine, maybe for different machines, or maybe for different shifts. That is also okay. Now the average range was found out to be 0.68 ticks. This is the average range. That means R bar is given. Calculate the action limits. How do we do it? The solution procedure. First, what we will write? What are the values which are given? First, you write what is the formula for action limit, upper and lower. Now you see what are the values which are given in the stated problem. So in this particular case, the values which are stated here, the values of mu s, the value of t plus minus 2, n, small n, 5 tests are conducted, so it is small n is fine, and average range is also given, that is R bar. So these are all given. We write the formula. Formula for upper action limit is mu s plus t minus 3.09 plus 1 minus 64 under root n into small a n R bar. That is what we have seen it earlier. So now in this case, you see now everything is given. So if everything is given, the only thing what was not given is the value of a n. Therefore, we need to consult this table where small a n is given and capital A n also is given. A table. Now for doing this calculation, you don't need capital A n. I can also do it using small a n as well. Now here, we find out what is the value of a n in this case. This is our n value is this. So small n is 0.43. So in this formula we write 36 plus 2 minus 3.09, 1.64 by root over 5, 0.43, and average range R bar is 0.68. So all this, the whatever variables are there in the equations, all those variables are given here. The values are stated here, all these parameters. Now it is simple calculation. You go step by step and you arrive at the figure 36.89 for the upper action limit. Same thing we do for lower action limit. We write the formula, substitute the values, and you get the result 35.11. That means the limits based on the modified tolerance, we can say. Modified tolerance limit is going to be 35.11 and 36.89. The actual tolerance is 36 plus minus 2. That means 38 and 34. But the modified limits based on sample averages is going to be 35.1 and 36.89 or 36.9. These are then become the two limits. These are modified limits. That is how. So this solution of the problem is easy. It is only what you may not remember or difficult to remember will be the formulas part. So if you understand the concept that how the formula has arrived, then you will be able to really write down the things very easily, that this is what must be the formula. Not that you have to really mug it up. If you understand the concept, you can have the formula on your own and you can find out the results. So this is how we can solve such problems. And with this discussion on control charts is now over. So we are not going to discuss anything related to control chart. And I hope now, for last I think 3 or 4 lecture sessions was only based on query control, especially on the control charts. So control chart is a very, very useful to keep the process under control. Today, because of our computers, we can easily make a chart. Data can be generated also very fast, process data especially, because most of the modern machines are also having a lot of gadgets with them. The data are generated and we need to only pool those data and then plot them in the form of a chart, and this chart could be also made dynamic in nature. As soon as the data come, the point is incorporated there, and we can see on a daily basis or any hourly basis also, or whatever you want, shift basis, how the chart is developing and whether any specific trend is being observed or not. And that is what is going to help you in terms of taking corrective action right at time. But what should be the corrective actions exactly, that needs a thorough understanding of the machines and the process. The statistical part is only going to help in terms of taking a scientific decision that yes, process has gone wrong and therefore some corrective action has to be taken. And what corrective action has to be taken, that will need a thorough understanding and knowledge about the process. So somebody who has a good domain knowledge only, he can only set the process back and in the right course. That is what is normally done. So let us close today's session. Thank you.